2 times the height of the Eiffel Tower, exactly the elevation reached by the road deck of the Huaiyang Bridge in China. The structure rises 625 meters above the water level, allowing drivers to literally pass through the clouds. It immediately set the record as the highest bridge in the world upon completion. But this is just the beginning. Why did the planners choose such an insidious location for construction? The landscape leaves no other option for a direct route across the canyon. The bridge extends through the gap, forming a bright bar suspended between the mountain peaks. At first glance, the project seems like science fiction, but in reality, it is a tangible achievement inaugurated in September 2025. One can notice how the engineering marvel cuts through the mist. The crossing quickly became a new icon of infrastructure. This audacious project has transformed into a solid reality. 92% of the surface of the province of Guo is made up of high mountains and impervious high plains. The journey of this bridge of records began in one of the most harsh regions of all China. 8 large rivers and countless affluents form deep valleys, cutting through the landscape and isolating communities. One can notice how the rugged terrain makes transport and trade a constant challenge for the local population. Therefore, the construction of the Oiji-Anlong Highway became a critical necessity. But this is just the beginning of the engineering struggle. The route connects the Opens with Anlong County, forcing its way through the landscape. It passes through the dangerous crossroads of the Baiyuan River inside the Gola of Huaiyang. Why was the Huaiyang Bridge created as a structure whose importance goes well beyond that of a normal bridge? During the investigation phase, the planning team faced a difficult dilemma. Engineers found themselves faced with 2 options with similar costs for the crossing. One option was to build a pleasant access road, but to place the bridge near the top of the mountain to reduce the span. The second option involved building the bridge below, but passing it through a series of steep and long galleries. In the end, they chose the challenge of about 250 feet. However, the V-shaped gorge created a distance of over 4,000 feet between the 2 edges of the rock. This is equivalent to more than 1,400 meters of open void. At first glance, standard designs seem capable of crossing this. But in reality, in these dimensions, all other types of bridges have failed. The most rigid and high bridge in the world could not have covered that distance safely, because the longest arch bridge could not have reached the other side, and even the largest suspended bridge could not have had the ability to cross the camp. Only a suspended bridge with an extra long main camp would have been able to satisfy these extremely severe engineering requirements. It gets more complex further on. So how do you build a huge bridge in such an impervious terrain? In principle, there are 3 steps to the operation. You start by building the 2 towers, anchoring them deeply into the stone. Then, you pull the 2 main cables in position and ensure they are screwed tightly to support the load. Finally, the bridge is hung using the suspension cables piece by piece. It looks outwardly simple on paper, but this is only the theory. In reality, everything is much more complex in the field. The Huygen Bridge towers 625 meters above the river. A 1,420-meter main camp extends across the canyon. If its tower structures are included, the bridge is comparable in height to the tallest artificial building in the world. With such huge numbers, it is clear that the Huygen Bridge is not only imposing on paper, it requires a construction process that goes beyond the standards of normal infrastructure projects. 24 huge cement elements anchor the bridge tower's heavy foundation. The infrastructure project faced a complex problem posed by the land itself, distinct from the structure above. Drilling had to reach deep into layers of rock and difficult strata. But this is just the beginning. Why was the local geology considered so dangerous for construction? The subterranean layers were full of cracks and dangerous aquifer faults. At first glance, the rock seemed stable, but in reality, even the smallest error during drilling could have caused serious accidents. Engineers therefore used a special system of piling to navigate the risks. One can notice how the machinery embeds the 24 cement masses deep in the ground. This material is combined with anti-seismic steel reinforcement for strength. It does not end at this stage. This ensures that the tower can resist the stress of decades of functioning. 262 meters, exactly the height of the taller main tower. The second column stands at 205 meters, acting as a primary anchor point. Why build them directly on the side of the mountain? Access seems difficult at such an altitude, but this elevation, hundreds of meters above the throat, is vital for securing the cableways. But this is just the beginning. Engineers erect these leading columns after finally overcoming the complex challenges of the foundations. The camera glides up the sheer vertical face of the construction. One can notice how the towers hold the bridge like giant pillars supporting a tape in the middle. Two weight cables, over 9,000 tons each, transfer the load. At first glance, the system looks static, but in reality, it actively balances tension. Therefore, stability is fundamental. High-resistance steel reinforces the frame to resist decades of operation. It is visible how the reinforcement strengthens the core structure. It gets more complex further on. The design must withstand strong winds, vibrations, and earthquakes. The massive anchors are now prepared to take the weight. 164,000 cubic meters of limestone form a massive block of extremely stable resistance on the Yanfang side. This gravity anchor rests solidly against the mountain slope, acting as a critical counterweight for the tension of the massive cables. The structure is engineered to withstand severe seismic activity, including powerful earthquakes, throughout its entire design duration. The Wang Bridge anchors function as gigantic counterweights that solidly block the two main cables in the mountains. But this is just the beginning. One can notice how the terrain dictates a completely different engineering strategy on the opposite bank. Instead of positioning a massive block of limestone on the surface, the anchorage on the Guanling side was designed as a tunnel anchorage. Engineers dug deep into the mountainside to reach the solid core. It is visible how the anchorage system is fixed directly to the natural rock inside the slope to secure the hold. Why was a tunnel chosen over a standard gravity block for this specific location? At first glance, replicating the Yanfang surface anchor seems like the obvious procedure, but in reality, the specific geography makes that impossible. Behind the tower on the Guanling side rises a steep mountain, but the amount of land available behind it is extremely limited. The cables transfer the entire tension of the bridge structure deep into the mountain itself. Therefore, using the mountain as a natural anchorage became the optimal solution for this section. It is visible how this method not only saves critical surface space, but also increases the overall stability of the structural system. The cable anchor system remains sufficiently robust to keep the entire structure in position until the huge towers can really exercise their strength. Thousands of meters separate the massive towers, creating a vast gap known as the deep throat. How is the first connection established across such a distance? Manual transfer is impossible in these conditions. Drones fly the first pilot line across, making the process of driving the cables safer and more precise. One can notice the thin thread tightening against the sky, but this is just the beginning of the assembly. Once the pilot line is successfully pulled, the passenger is lifted into place. This component creates the foundations for the temporary walkway suspended between the towers. At first glance, it seems like a simple platform, but in reality, it is the workspace where operators will build the entire system of cables. Thus, the site enters the biocritical phase, ready for the construction of the two main cables. 5.7 millimeters is the precise diameter of the high-resistance steel wires that form the backbone of the entire structure. These slender elements are intertwined with absolute precision to create the two main cables, which constitute the most important phase of the Rava Trent project. The rear spina serves as the main point of the entire bridge system. Tens of thousands of individual wires merge here to support tens of thousands of tons of load, creating a massive safety margin. But this is just the beginning of the complex assembly. Workers maneuver on a half-air suspension footbridge to position the strands. Why is continuous satellite monitoring required during this process? Visual alignment might seem sufficient for such large components. However, GPS supervision is strictly necessary to maintain an alignment error lower than 2 millimeters between the two anchor points. At first glance, pulling wires forward and backward seems like a simple mechanical task, but in reality, it requires managing every turn under the pressure of strong winds. One can notice how the cable strips, each made of 91 steel wires, are guided with extreme care at an altitude of thousands of feet. The control of every movement is of fundamental importance to ensure structural integrity. It gets more complex further on. Once all 218 turns are finally installed, the loose bundle undergoes a transformation. A cable compacting machine engages the material, connecting the strands into a perfectly circular cable using a special compression process. It is visible how the mechanism travels along the line, forcing the steel into a dense, unified mass to eliminate voids. Afterward, the cable is wrapped in several protective layers to resist corrosion, intense colds, and constant vibrations for decades. Only when these two huge main cables are fully completed is the bridge ready for the deck to be suspended in mid-air. 2,000 feet. This is the altitude above the water where the bridge enters its decisive phase. Once the two main cables are completed, the focus shifts to suspending the deck in mid-air. Why install a vertical slat system before the roadway itself? It appears to be merely a connecting step, but these special slats are vital, capable of resisting thousands of tons of force to transfer the load from the bridge floor to the main cables and distribute it to the two anchor points. But this is just the beginning of the heavy lifting. Heavy machinery hoists the 93 steel segments, lifting them one by one from the center of the span. One can notice how the structure gradually extends outward toward both sides as the heavy blocks rise. Each segment boasts 100 tons of weight, requiring immense power to position. At first glance, attaching them seems straightforward, but in reality, engineers must constantly adjust the cable flexion and tension in the slats. The segments are welded using a system suspended more than 2,000 feet up, connected through special bearing joints. It gets more complex further on. The team meticulously monitors the position of each panel to ensure the floor remains aligned without tilting or twisting under the forces of the wind. It is visible how the steel skeleton solidifies into a continuous form. Once all 93 segments are positioned and connected in a unified structure, the upper floor system is finally built. This process transforms the suspended steel into a completely functional highway. The massive crossing is now ready to support traffic. 96 heavy trucks rolled onto the fresh asphalt to challenge the massive structure. In August 2025, the construction phase officially concluded, giving way to the evaluation of actual resistance. A total weight of 3,700 tons pressed down on the spans to test carrying capacity. It is visible how the heavy vehicles align to create the necessary dynamic stress. But this is just the beginning. The fleet positioned itself with calculated precision. Why subject the newly built spans to such extreme pressure immediately? At first glance, placing thousands of tons on a fresh structure seems dangerous. But in reality, this load test is essential to ensure the bridge meets the most severe safety standards. One can notice how the structure settles microscopically under the burden of the convoy. Over 400 sensors recorded every shift, capturing data on deformation, oscillation, and vibration. This real-time analysis not only confirmed absolute safety, but also demonstrated innovations in structural monitoring. The equipment tracked the dynamic performance continuously, the bridge successfully passed the exam, proving its readiness for future operation. Level 14 on the Beaufort scale represents a wind force capable of tearing structures apart. The Huaiyang Gorge is known for these punishing winds during favorable seasons. Why must the construction be interrupted every time the winds reach level 6 or higher? It seems the bridge could withstand far more extreme conditions, but without this strict limit, the safety of the workers would be compromised by the unpredictable gusts. The transport of steel beams into the installation position demands intense physical effort in this harsh landscape. One can notice how the stabilizing structures sometimes crumble, forcing the workers to straighten them manually. It gets more complex further on. They must maintain the lines in equilibrium between the sides of the mountains and valleys to reduce the minimum risk of torsion. They start working at 6 in the morning and often do not return before sunset. At first glance, the material supply seems like a standard logistical task, but in reality, the volume is immense. The adjunct bridge requires a total of 439,000 cubic meters of limestone. This volume is the equivalent of 176 Olympic pools poured into the gorge. To reduce costs and protect the environment, engineers reuse the waste rock produced during construction. Heavy machinery breaks the debris into high-performance green mineral powder. The process is only gaining momentum. This powder is used as additional material to replace 20% of the cement in every cubic meter of limestone. This approach not only allows the project to save cement, but also uses the waste rock fully. One can see how this contributes to limiting pollution and preserving natural resources. Thus, the construction team overcomes the challenges to deliver the project in a sustainable and efficient way. 1.5 hours is the time it now takes to travel from the bridge area to the city of Guangzhou. In the past, this same route required at least 3 hours of driving. The completed structure saves almost half the time, conquering the mountains and rocks that once isolated the territory. Speed makes life more comfortable for local residents, but the benefits extend to thousands of other people in the area. But this is just the beginning. Why include tourism elements in a critical transport project? The primary goal is usually just movement. Yet, the Huajiang Bridge was designed from the start to ensure both structural integrity and a unique experience for visitors. One can notice wide views and ideal elevations that frame splendid scenery on both sides. At first glance, the pavement seems ordinary, but in reality, a specialized road coating stabilizes the bridge while supporting high-quality adventure sports. Safety rings are equipped along the edges to protect participants. Inside the steel cross lies a walkway. If not built for tourism, this corridor would simply serve as a maintenance passage. It gets more complex further on. The bridge opens up regional commercial routes between China and Southeast Asia. This connection actively attracts investments and creates jobs across the sector. Improved transport facilitates better healthcare and healthcare assistance for the population. Tourism brings the entire region closer to a prosperous future, marking a shift in economic dynamics. Thousands of tons of materials converge to create the Huijiang Bridge, which stands as the culmination of engineering intelligence. Why was every phase executed with such absolute precision? It might seem that a massive structure could withstand minor deviations. However, the tensioning of suspension cables relies on exact alignment to hold the weight without failure. From the very first days of deep drilling into the rocky road, the effort required total dedication. The process is only gaining momentum. One can notice how the cement settles to form the heavy beams of the towers. The main completion of the tower peaks signaled the readiness for the installation of steel transversal rails. Assembly of every locking component followed, securing the integrity of the span with calculated force. At first glance, the bridge seemed to grow effortlessly day after day from an idea on paper, but in reality, it was a struggle against the deep canyon to create a masterful reality. This project represents not only the history of a world record, but also a testimony to the transformation of the province of Guizhou. A region once known as a remote and harsh land is now fully integrated into the modern rhythm of the 20th century. Human perseverance has successfully given life to an engineering feat once considered impossible.